Hello, I'm Pascal Thubert. I'm a R&D engineer with Cisco Systems, and I've been with the IETF for pretty much 20 years, working on IPv6 standards for mobility, for wireless, and for the Internet of Things. I'm here today to tell you about a new effort that we are starting at the IETF. It's called RAW. RAW stands for Reliable and Available Wireless. And I've put you on the link here, on the page here, a link to the data tracker at the IETF where the data about the RAW working group is being held. And when I started working, I was with IBM at the time, so it's almost 30 years ago. I was using 4 different types of networks to do my daily job. I was using plain paper mail if I wanted to send, for instance, a side paper or receive some hardware documentation. I would use the plain old telephone system, so the PSTN. For instance, when I was on the move in the US, I would call my wife from the hotel, and because it was a long distance call, then it would be very, very expensive, so I could not stay long talking to my wife. I loved at the hotel to watch Star Trek, but if I wanted to record it to bring the tapes back home, then I actually needed to buy a VCR, and I did. I bought a small VCR from Walmart, and then I could record my favorite shows and bring them back home. But then I had to buy a special TV because my old TV would not play NTSC, which was the standard in the US, versus PAN-SECAM in Europe. And last but not least, I could actually access data network from IBM because IBM invented SNA, which was the original corporate network that we had at the time before IP and Ethernet came in. So basically, I ended up working with 4 different networks, which meant having people operating those 4 networks, having to buy specific hardware to use this network, and at the end of the day, a very expensive operation. And the internet came in the 90s and changed everything. The email became free and almost zero latency and high volume. You can send so many emails, right? But the unexpected benefit that came in with it is, for me, the capability to maintain archive. With my archive, I can actually dig 10 years ago if I like and find an email I sent at the time. Unexpected benefit from the convergence of mail over internet. Voice also converged and same. I mean, it became mostly free, but then unexpected benefit. I ended up with video and conferencing, and again mostly for free. TV converged, and guess what? I can watch TV on my computer, which was not imaginable in my first years of work. And not only can I see TV on my computer, I can also talk to people and participate to the show. For instance, there is the confinement now with the COVID, and guess what? The yoga coach can actually talk to us and have us do exactly as if we were actually visiting in the sports room. And last but not least, the internet brought in a new breed of devices for what we call the Internet of Things, and with that the capability to save, for instance, the way we consume energy. So we see savings, we see free services, and we see unexpected benefits. All this because we converged a number of networks over IT technologies, over IP. Now there's one kind of network which has not converged to IP. And that's a critical one, right? It's the world of automation. So yes, you see Ethernet and IP more and more and more in the factories, for instance, with new standards such as CIP from ODVA, and you see that most of the major factory types of technologies are bringing Ethernet in the party. But the core of the automation network itself has not converged to IP. And the reason why is that IP and IT technology, right, are based on stochastic, quote-unquote, best effort transmissions. And what the automation guys really want is a network that will operate over and over and over in exactly the same fashion, guaranteed. This is what we started looking at, say, 5 plus, almost 10 years ago, when companies like GE, Cisco created what we now call the industrial internet. And the observation at the time was that if you could do just 1% optimization on your process, you could save over 15 years, as you can see on this picture, something like $90 billion just for the domain of oil and gas. Now think about the smart grids, think about cars, think about planes, think about healthcare. So we had all those numbers, and all you needed to do is save 1%. And how would you save 1%? Well, by applying IT technologies such as big data, artificial intelligence, etc., to your industrial process. But you can only do that if you have placed all those processes over IP. And you can only place those processes over IP if the IP network can provide you the service level agreement, the SLA, that is required for the automation. So the typical flow that you will find in automation is what we call a control loop. So a control loop is, I've got this sensor captures some physical domain measure, and you have to send it to some logic, with typically what we call a PLC, programmable logic controller. The programmable logic controller, the PLC, will make some computation and decide if you need to change the world. And if you need to, then it will send a command to what we call an actuator, which will do something like higher temperature, lower the temperature, etc. Well, a control loop happens periodically, and the period can be very short. It can be hundreds of times per second in factory automation. And the network has to deliver over and over and over the packet within a bounded latency so the control loop can have its normal activity. This is not the way a classical packet-based network operates. A packet-based network operates in what we call best effort, stochastic way. Statistical multiplexing really means that you get packets from everywhere, and you have to send them over your outgoing links, and too many packets may end up at some point of time converging on one outgoing link, meaning that the queue for that link will build up, causing more and more latency, and eventually causing drops if the queue goes too high. Those drops are called congestion loss. This increased latency and the congestion loss are not acceptable in the domain of automation. You have to deliver your packets over and over and over within a bounded latency. So to measure the reliability of a network and the availability of the network, we had to define terms, and we took those terms from the industrial, trying to keep pretty much the same meaning. And so for RAW, by reliability, we mean the capability to provide the system level, service level agreement that you agree about. For instance, a bounded latency of 1 millisecond for every packet. And failures to deliver the packet within that millisecond means that the packet is as good as lost. Now, a control loop can always lose one packet. I mean, that's a fact of life, so packets get lost. What can't happen, what is not allowed to happen, is several packets in a row. Because if you lose several packets in a row, your control loop may become unstable, and you have to end the system in emergency stop. And guess what? People really don't like that. So we measure basically the number of consecutive failures in .NET terms. That will be the maximum consecutive losses, and that's an important metric for establishing the reliability of your network. The second thing we care about is the availability, which is basically the ratio of uptime over total time being uptime plus downtime. Now, if you consider a wireless link, and that's really the focus of RAW, you'll find that a given single link will never be able to give you availability all the time, a high degree of availability, because there will be objects passing in the Fresnel zone, there will be interferences, and there will be multipass fading, all sorts of effects that will sometimes affect your transmission. So we see that we'll need several parallel links of radio to provide high availability. And that's what Row really will be dealing with and optimizing.